Okay, some of you may know that I've been messing with slingshots for a long time. I make them and I shoot them. And one of the projects I had was to understand the physics enough of them in the real world way so that I could predict the speeds that I would shoot a slingshot at if I knew about the rubber. So if you know how much force it takes to pull the rubber back and then release it, you should be able to calculate how fast the projectile would go. And a few years ago I published some stuff that showed that indeed you could be pretty successful at that. It turns out the measurements of taking force versus distance of draw are pretty slow going, and yet need to be done quickly, because when you let go of a slingshot, you're not going like this. It's a real fast shot, and so you want to do those measurements as fast as you can. So both because there's a lot of measurements and it's convenient to automate it, and because you want to do the measurements as quickly as you can, I put together this automated setup for measuring the force versus draw for slingshots. There was a secondary motivation too, and that was that I got a Christmas present of an Arduino, which is like a microcontroller that's behind letting you do all this stuff. So first what I want to do is I'll just show you how it operates, and then I'll show you some of the special features. So I'll go over to the computer here. There's actually, you could think of two computers involved. One is a laptop computer, and the other is this Arduino that's hidden over here, which is really not a computer as much as a instrument controller. Okay, so I'm at the desktop computer and I'm going to get it going. This is a sled that's going to go up and down this track, and you notice that the sled's attached to this rubber band, and as the sled moves, the rubber band will stretch, and we'll be able to get some force versus pull distance information. Okay, I'm going to follow the directions on the computer when they're telling me to click things to get going. And when I do, this sled's going to first go slamming backwards, run into this limit switch here, and then, which is a kind of a safety device, and then go back to a certain mark on here. So let's get going. It's compiling and downloading, so it takes a little bit. Okay. And now it's telling me to adjust the position of the sled if I want to. It's a little hard to see from there, but there's a little line on here penciled in across these aluminum rulers. And there's a joystick over here which you also can't quite see. But if, you see the sled moving as I do that. It turned out it was perfectly lined, so I didn't need to do that, but I did it just to show you. Okay, so that's aligned. And it tells me when I like the position of alignment to hit a switch. I did. And the next thing it's asking me to do on the computer is to move the sled to the position where there's no force on this rubber band. So I'm just going to move the sled back until it droops down and touches the wood there and call it good enough. And I'll enter the force. And now it's going to start taking measurements. There's some timing things that happen. So first it's stretching out the rubber band by a factor of 2. It's called a stretch factor of 2, which means the stretch length is twice as long as the unstretched length. And you saw there that it jumped in about 1-inch increments. Now it's going out to a stretch factor of 4, and it's going to come back in 1-inch increments. And next it's going to go out to a stretch factor of 6, and then come back. And it's way out there. Now it's going to come back. I don't know if you noticed, it came back to about here and then jumped backwards. And that was an extra jump step I put in there, telling it to go back to where that line in the across the ruler was. And that's put in there to check to confirm that it goes right on top of that line. And if it does, it means that these pulleys and the like didn't lose a grip, and so that the position accuracy is just what we wanted it to be. And I can see looking down here that I'm just dead on that line there, so there was no slipping. I haven't mentioned how you get some of these readings of force versus draw distance. The draw distance, which is the distance along here, is known not by measuring it, but because you have a stepper motor here. And this stepper motor moves in very precise steps. And each step is about 1/100 of an inch travel, so it can be quite precise. So here we have the stepper motor, and it's got this pulley on it that goes around, and it turns this it's called a timing belt. And I don't know if you can see it quite, but there's little ridges along here, and each of those ridges are about 2 millimeters apart. You can think of those as being like gears, and this is a very non-stretching kind of rubber. It's got either metal or fiberglass inside it to make sure it stays that way. And so this belt eventually connects to this sled, and so when the belt moves, the sled will slide up or down this track. This track is actually kind of conveniently made by having these two 4-foot long by 1 5/8 inch wide aluminum measuring sticks that you can get at Harbor Freight for $5 each. And they're just screwed onto a board, and the board can be a piece of plywood or a regular piece of pine or whatever. And the board doesn't really contact the sled, so it can be kind of rough edged and it wouldn't matter. But it's quite cheap to make this track, and the variation in the spacing across this pair of metal rulers is only 1/1000th of an inch, plus or minus, over the whole length. So it's really quite precise. Let me go down to the other end and explain what this. Well, maybe just magnify it. In that little wood assembly there, there's some little pulleys, and those are the return pulleys. They're not powered like the gearing on the stepper motor. And you also notice that there's a little blue box down there, and it's got an arm on it, and it's the same as this little blue box. And this is called a limiter switch, and you see it's got a little pulley on it, and it can move one way or the other. And what happens is if for some reason we made a mistake and this sled came zipping down here, we wouldn't want it to crash into everything. So this limit switch senses that kind of event and would stop the sled in a ½ inch or something. So that's kind of a safety feature. I actually have a little crash barrier here too, but it's never come into play. Okay, so I said I'm measuring force versus distance. We got the distance part from using the stepper motor and that special belt. And the force part of it is measured. Let's get over here. You see this little metal thing right in here. That's actually a resistor that's being pulled from opposite sides, and that bends things a little bit, and it turns out it makes a very sensitive force measuring situation. And it's a commonly used type of measurement, and it has one good aspect that it's not like a spring where it actually stretches out to reflect a force. It really stays the same length for practical purposes. And you'll notice that there's wires connected to that resistor, these fine wires. And there's a little circuit board here, right, that green thing, and that's what interprets the resistance and changes it into a force. What are the other things on this table? This green section with all the wires going to it is a cover for the microcontroller, which is called a Arduino Uno, and the circuit board for that is about the same size as this green cover thing, and the green cover thing just provides a way of screwing wires into place instead of just inserting them in a slot and hope they don't move around. The rest of I mentioned the stepper motor already. That's this guy, and it's driven by this special driver. It's costs about $35, but it's worth it. And the stepper motor costs about $35. And the stepper motor also needs its own power supply, which is this guy. And I was able to get that for $18. So the equipment down here is not that expensive. The other thing I might point out is this joystick, and that when it's ready to listen to me, it could move the sled up and down. Here's the little switch I use for entering information when I'm prompted that way. And then I have this emergency stop button if things go awry, and it can stop it kind of gracefully. There's a couple things I wanted to mention that I might have forgotten by now. We also measure the temperature whenever we're doing these measurements, because it turns out the force versus draw distance is somewhat sensitive to the temperature. So that's this little circuit board right in here. It's pretty straightforward to do. And then the other thing I wanted to show you was this gadget here, which is called a tensioner. The metal piece here, you could buy for a couple bucks. They're called either cable tensioners or rope tensioners, and they kind of latch into a little loop on the end of the two belts coming in, the screws here have opposite threads, left and right hand, and so as you turn this one way or the other, you either loosen or tighten the tension. And what had been commonly mentioned by various people is, instead of having this metal tensioner, people have been using just plastic zip ties. Well, I found that with plastic zip ties, that they work okay if you're not pulling much force. But by the time you start pulling 10 or 15 pounds with the sled pulling on the rubber, it doesn't work very well, and you find that the gears start to slip, and you would then lose track of your distance. Replacing the plastic zip ties with this thing has been great. I have no trouble now, and I can see how tight things are, and adjust the tightness in a way that's going to not slip around and vary. I don't know how many pounds of tightness there are, for instance, but I have a little olive can, I think it is, that I rest on this top belt here, and you see the two belts are about maybe 2 inches apart, and if I balance that olive can on here, it goes down about halfway, so I can at least reproduce the tension by targeting that kind of a stiffness. This figure shows the kind of data that is collected by the automated slingshot force versus draw system. You'll notice that there's a number of different curves typically, and in a typical case you'll start from a position of no stretch and no force, jump all the way in one step to the biggest amount of stretch and force on that group, and then work your way backwards on the reverse draw. And then once you've gotten back to zero force, and you jump to the next biggest stretch and work your way back, and so on. You'll notice that the force depends on more than just how much you stretch it. For instance, this force here is about 10 pounds, and it occurred at a stretch factor of about 4.3. But you see that there's other curves here that have the same amount of stretch, but they have less force than this. So for instance, this curve here, which starts at a stretch factor of 5.4, by the time you get back down in the reverse draw to the same amount of stretch as this guy, instead of being at 10 pounds, it's at 6 pounds. Because the force depends not only on the amount of stretch, but also on the stretch history, there's a lot more data to be collected than if it did not. So instead of just having more or less the red points to collect data for, we have to collect data for all these other different cases, and that makes it a lot more time consuming and a lot more important to try to find an automated process for doing this.